Okay, today we'll begin our study of wave motion. So what is a wave? Wave is basically just a transfer of energy. For example, you're adding energy to this spring by shaking it up and down. Some waves require a medium to travel through, and they're called mechanical waves. And an example of that would be sound. For example, you can't transfer sound through a vacuum. Some waves don't require a medium to travel through. An example of that would be like electromagnetic waves or light waves from the sun. Light waves travel through a vacuum to get to us, so they obviously don't need a medium. Okay, there's a few basic types of waves, and the first one we'll study is called transverse waves. And with the transverse wave, the vibrations are perpendicular to the direction of motion. So let me show you what I mean by that. In this case, you produce a transverse wave by moving the string or the medium up and down. And as you're moving it up and down, it creates a wave. And that wave travels this direction. So the displacement is perpendicular to the direction of motion. And in this type of wave, there's the high points called the crests, the low points called the troughs. In the drawing, one cycle is shown in the shaded color. The amplitude, right here, is the distance from the undisturbed point to the high point, and the undisturbed point to the low point. They're both called the amplitude. And the more energy you add to it, the higher the amplitude would be. Wavelength is the distance that it takes to complete one cycle. And period is the time it takes to complete one cycle. And as we learn from simple harmonic motion, period and frequency are reciprocals of each other. Alright, so now let's talk about what's called a longitudinal wave, or sometimes it's called a compressional wave. In this case, the displacements are in the same direction as the wave travels. For example, you're moving your hand in and out like this, and the wave travels in the same direction you're moving it in and out, or in the same axes, in other words. So if you take your hand and you push it in, you can create an area of high compression area or a condensation, and it will travel through the wave. And as you pull your hand back out, it creates a stretch region, which is called a rarefaction. And if you take the distance between any two, like from a rarefaction to a rarefaction, that would be a wavelength. Or from compression to compression would be a wavelength. Water waves are kind of interesting because they're both transverse and longitudinal at the same time. It has a transverse component going up and down, and longitudinal going back and forth. And it creates a circular motion. That's why you see the rolling waves. Periodic waves consist of cycles or patterns that are produced over and over again by the source. In these figures, every segment of a slinky vibrates in simple harmonic motion, provided the end of the slinky is moved in simple harmonic motion. So if you're moving your hand up, mimicking simple harmonic motion, you'll create a wave pattern that's simple harmonic motion. And the same thing is true here, moving it in and out, a compressional wave that's following simple harmonic motion. Alright, so let's talk about the velocity of a wave. Well, we know that velocity is just basically displacement over time. Right? So with a wave, what can we think of as the displacement? Well, obviously the wavelength, because it's the distance of one cycle. And what can we think of as a unit of time? Well, the period. So therefore, we have the equation that velocity is equal to the distance over the time, or the wavelength over the period. And remember that frequency and period are reciprocals of each other, so we can also write the formula in this fashion. So let's try an example. AM and FM radio waves are transverse waves consisting of electric and magnetic fields disturbances traveling at the speed of 3.0 times 10 to the 8th meters per second. station broadcasts an AM radio wave whose frequency is shown here, and an FM wave whose frequency is shown here. Find the distance between the adjacent crests. So that's really just a fancy way of saying what's the wavelength. So we know that we have the formula that velocity is equal to wavelength divided by period, or frequency times wavelength, and we're going to solve that for wavelength. In this case, I used the frequency form of the equation because that's what was given to us. Alright, so for the AM radio wave, I put in the speed, and I put in the frequency, and I'm given the wavelength. Notice that the speed is in meters per second, and hertz is really 1/2 so the seconds cancel out and you're left in meters. Also notice that the higher the frequency, so in this case it's a very high frequency, the lower the wavelength will be. So this has a lower frequency, so a longer wavelength. And that's just a simple introduction to waves.